Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about why I like using the JONSWAP wave spectrum in ProteusDS analysis so much. So when you create a new project and you want to see what's happening to floating systems in wind waves and currents, you'll see under wave type there's a couple of different spectrum options by default, the Pearson-Moskowitz and the JONSWAP spectrum. Of course, there's custom options, but if you want to get up and running and you don't have a lot of information, you got to pick one of these irregular sea states. Often people say the Pearson-Moskowitz is better representative of what you might find out in a fully developed unlimited fetch condition that's like way out in the middle of the ocean somewhere. And JONSWAP's a little bit better for sort of coastal environments where there's limited fetch and that sort of thing. But you may notice that JONSWAP comes up a lot, and we use it in a lot of the examples. And really, there's a simple reason for that. If you go and look at the documentation, in the definition of the spectrum functions there for Pearson-Moskowitz and JONSWAP, the difference is the JONSWAP has this nice little shape factor here, the non-dimensional peak shape parameter, which allows you to customize, if you want, you don't have to do this, but it allows you to customize how peaky the spectrum is. And in fact, if you change this value to 1, it gives you the same thing as the Pearson-Moskowitz spectrum. So that's nice and very sort of analytical, but what does it mean when you're looking at a floating system response, and what does that look like? Well, let's look at a quick example here. First off, just looking at the spectrum, so be aware the outputs here are available in simulation. You can look at the as simulated spectrums and plot them. Here we have one with a gamma function of 1. That's the Pearson-Moskowitz basically. Here's the default value, gamma value of 3.3 in green, quite a bit more peaked here. And what happens is you'll see a lot more wave energy and wave response kind of focused around that peak period. And then gamma value of 5 has even more energy kind of focused around that peak period. And another way of thinking of this is that if we had all the energy focused at one frequency, you'd essentially have a perfect sinusoidal wave, an airy wave. So just looking at the sample input here, you can see we've got that peak shape constant value here. Now, I've set up 3 simulations with no wave spreading just to make it a little bit easier to see. And we have the gamma function of 5 here, 3.3 here, and then gamma function of 1 here. And then the camera settings are all the same here, so we kind of get a similar view of what's happening. So generally speaking, what you'll sort of notice is you see a little bit more definition behind the wave function, the sea surface here when there's troughs and crests at different frequencies. And in this one, on the other end here, it's a little bit smoother, but you're getting a little bit bigger waves around that kind of main, period. It's a little bit of a detail. It doesn't mean that it's important. You need to look at this all the time in every single scenario that you're considering. But it's just nice that the JONSWAP spectrum gives you that flexibility if you want to change that and see what happens. It's definitely a nuance, but offers a lot of flexibility in this kind of investigation. So, you can see, for example, here's this trough coming through here. It's a little bit more smoothed out in here, but it's a pretty subtle difference between the different scenarios here. So, hope that helps give a bit of an illustration and highlight what the peak shape factor does and why it's nice to have that as a bit of a flexibility when working with the JONSWAP spectrum. Thanks for watching.